Okay, good afternoon, everyone, and welcome to this week's Sustainable Fuels webinar from Energy Futures Lab. My name is Conor McNally. I'm the Communications Manager at the Institute, and it's my pleasure to welcome this week's speaker, who is Dr. Oytun Babacan from the Grantham Institute here at Imperial. Oytun's research focuses on the integration of energy storage, electric vehicles, and renewable energy generation into existing infrastructure. He also investigates carbon mitigation pathways with a focus on energy and environmental impacts of emerging technologies, such as decarbonised liquid fuels. Previously, he worked on a range of different projects at the University of California, San Diego, including solar resource forecasting using sky imagers, grid-connected testing of battery modules, and energy system modelling of cities and microgrids that heavily adopt solar photovoltaics. And he completed his graduate studies in mechanical engineering at the University of Illinois, Urbana-Champaign, and the University of California, San Diego. So we're delighted to welcome Oytun here today. He's going to speak for about 30 or 40 minutes, and then he'll have time at the end to take some of your questions. So to submit a question, use the Q&A box, which you'll find on the right-hand side of your screen. And as I say, we'll come to those immediately after the presentation. So with that, I'll hand over now to Oytun.
Thanks, Conor. Hello, everyone. As Conor introduced, I'm a research fellow at the Grantham Institute. I'll just quickly make my screen full. If Conor, can you confirm that it's just full screen and you can see the cover?
That's perfect.
All right. I will be talking about carbon abatement energy of low carbon fuels today as part of the Sustainable Fuels webinar series. And we'll be touching on a couple of different issues related to sustainable fuels as well. And roughly, we will start with talking about climate change mitigation options and actually how we could measure their performance so they can deliver the results we want. We'll briefly talk about how we can actually categorize those technologies, and sustainable fuels can go into different buckets, as we will see. And then I guess main part of the talk will be based on the carbon abatement of energy of fuels. This will be a part of our recent study on looking at the feasibility of different carbon dioxide mitigation options. You can see the paper there, and the underlying concepts were first published there, and we're still building on top of that. So that will kind of go into the discussion points on what we do and what other people can actually do, and hopefully we'll have some questions from you as well. So to start, it's important to understand the context and why we are interested in this technology. So by now, human activities are estimated to have caused approximately a degree of global warming, 1 Celsius degree. And we are likely to reach 1.5 in the next decade to 2050 timeline. And the Intergovernmental Panel of Climate Change laid down this targets to limit the warming to 1.5 degrees a couple of years ago. And they kind of talk about 4 iconic cases where like these pathways that can help us achieve this goal. And you can see kind of from left to right, the P1 kind of depends on rapidly decarbonizing and depending on natural solutions to kind of suck these residual carbon dioxide, all the way to the P4, where you depend on a lot of carbon sequestration capabilities that you have to develop in upcoming decades. So with regards to that, the thing here is, obviously we need to find the carbon capture technologies and which ones will work the best on the fields. But apart from that fact, it's basically an economic and political issue, and how you can actually integrate existing technologies into the system. But the choice that we have is from the left to right again, is whether you depend on kind of the low energy demand scenarios and you rapidly decarbonize your energy supply using what you have, and all the way to you try to find technologies that will help kind of keeping the high resource energy expenditure economy. So looking at the spectrum, then we have to understand where we need mitigation, regardless of the choice that you make. So here on the pie chart, you're seeing somewhat outdated emissions graph, but it gives you the meaning. Is we have some sectors that we have solutions to decarbonize now, and there are some others that you can see with the longer pies that are harder to tackle even with today's technology. So we need new innovative solutions to take care of them. And part of these sectors are inherently linked to sustainable fuels that we will talk about. So for instance, long distance transport, heavy duty transportation, aviation, shipping examples, and also iron and steel and cement industries, which are relatively difficult to decarbonize at the moment. Here, the understanding is the challenge underlying here is you either have very specific applications that need very high quality heat, for instance, the steel production, or you need very densely packed energy, and usually mobile in the case of aviation, for instance, and you need these sources to be non-fossil fuel. So that's kind of the challenge here. So when you kind of lay down the plans for a net zero energy system, then it might look like this, where you see the blue circle where you kind of input the system with a lot of decarbonized electricity, a lot of energy that doesn't depend on, well, that doesn't correlate with carbon dioxide emissions. And you need fossil feedstock in an alternative form. So we still need some carbon in the system because that's how we kind of operate the rest of the industries. So the red point kind of illustrates that. So once you figure out how you do blue and red, and the remaining is basically converting energy and materials into each other. Obviously, every step that you take will be coming with some inefficiencies in the system and some useful energy losses. So that is another challenge as well. So then when we kind of reconsider the four pathways that we saw in the earlier slide, so from this left bars, we are trying to transition into something else. And if we need additional technologies to mitigate carbon dioxide, this could be in the form of carbon, low carbon sustainable fuels, you might have to add in more energy to your system, well, you might have to spend more energy, and that will be a big bucket of your future energy use. So we need to be aware when we're building these net zero energy systems, how much energy have to be committed into these technologies. So then the question is how you can actually measure the benefit of different options, because obviously we don't only have a single fuel type to go forward with. So apart from the technical side of things, for instance, some systems might be inherently compatible with one fuel type. There are other ways of looking at it as well. And I mean, the kind of the economy side of things might start with, for instance, marginal abatement cost metric, where you basically define a price for the carbon dioxide that you were able to get out of your system. And in this case, it's basically our atmosphere. And then you can kind of rank different measures from A to F to N and see which ones are relatively better in economic terms at some point of your analysis. So these are good if you use them along with other policy tools, not just as a single way. And what you can achieve is then you can kind of look at the whole horizon, whole options, and you can rank them and basically say, okay, we'll try to do the cheapest or the most beneficial first, all the way to the other. So the question that we will try to answer here is if we can actually define the same for in the energy terms. So basically some kind of marginal metric that will help us rank all these systems, but in terms of their energy requirements. So in terms of technologies that are spending energy from our energy buckets. So a simple way is to basically lay down the process or technology, like you see in the diagram here. This process might require energy, or maybe it's actually producing energy. Like if you burn coal, it might produce energy, but also emissions. Or a different process might basically get this carbon dioxide out of the system because maybe it's using it as a feedstock in the first place. For instance, if you're embedding the carbon dioxide into your fuel. So then you can basically do the carbon and energy accounting and come up with this carbon abatement energy that we will introduce more in this talk. So non-fuel perspective of this is, for instance, if you look at switching to a better lighting in terms of energy efficiency, like LED, you might see that this is actually quite nicely aligned with what you want to do. You're spending, well, actually you're gaining because of the energy efficiency measure. You're gaining energy per carbon dioxide that you abated in this case. Or another example would be if you switch to renewables from coal or natural gas, what is the energy cost to your society is very minimal in this case. So then you can see how the two graphs can actually help you decide on things, both the economics and the energy perspective. Of course, there's an inherent relation between them, because if you spend more energy, that's usually more costly. But the market dynamics don't always work like that, because you have subsidies in place or other measures that might change the cost of particular energy sources differently for different purposes. So by looking at the energy accounting specifically, you're basically avoiding the market impact on your decisions, because you universally know how much energy should go into that process, regardless of its price. So if we kind of turn our attention to this concept of, okay, how much energy I have to put in, or how much energy I can get out of this system, depending on the carbon dioxide mitigated, then you can make some decisions. So the usual thing that we look at is, okay, what are our alternatives and what is our starting point, so our reference points. This is important because this type of relative metrics, they obviously need a baseline or incumbent technology, because we are not just looking at how the technology performs, but we are trying to understand the relative benefit, the relative performance improvements from that new technology. So if you look at kind of this carbon balance to energy balance diagram here, so you have a starting point for your reference case. Alternative one is basically saying that it's perfect. You're basically reducing your carbon input to the system, and also you're actually spending less energy. As a different alternative, if you go to the number two, you are even reducing the carbon balance even more, but then now you actually have to spend a bit more energy. So obviously these are hypothetical cases, but this is basically telling you how different alternatives can help with decisions. So then you end up with different scenarios. Obviously, we don't want to go to unviable region where you actually increase your carbon balance and you increase your energy balance. At least in terms of these two metrics, it's not beneficial to the system at all. We want to go basically to preferable or possible scenarios, but there are other things that can happen as well. For instance, you might actually increase your carbon balance, but at the benefit of gaining some energy, and maybe a different technology that could work on the side can help you reducing the carbon balance even more. So kind of collectively, you can address the mitigation issue as well. So it's basically the analysis depends on the routes and how you build up your system. So that's how you should compare them as well. The final note here is there's the unviable at scale note on the right side, the bottom right figure. That's basically if a system is able to remove carbon, but if it spends so much energy that the society cannot possibly afford, that is why you could end up in that region. Basically, you might not be able to afford because your energy budget is not high enough because of resource limitations or other concerns you might have. So then we can, with this thinking, we can categorize the mitigation options and kind of start to put our fuels into different buckets. So one is carbon avoidance. So some of the options I show here is not maybe directly relevant to fuels, but for instance here, you're seeing that conventionally you're producing electricity from coal, you switch to the alternative, you're producing electricity, and obviously you might use it in electric vehicles or other direct electrified transportation options. So these carbon avoidance measures, they are basically the measures or changes that you take in order to reduce your dependence on fossil feedstocks or fossil fuels, or both. So they typically require some kind of renewable or like low carbon energy generation, but you could basically come up with energy efficiency measures. For instance, for electric vehicles, you might reduce the weight of your car. You might come up with different aerodynamics, and that is reducing the energy needs, and that's also is quantifiable by this perspective. Another category is carbon embedding, where you use the carbon dioxide either coming from atmosphere or other sources, and you use it as a fossil feedstock. So you basically embed that molecule into the product that you use, and that way you try to limit your fossil fuel dependence, or fossil feedstock dependence in this case. And for instance, in the case of methanol, the usual way is you hydrogenate the carbon monoxide with hydrogen, and you obtain methanol. But the alternative way would be actually the direct hydrogenation of carbon dioxide or other routes to utilize that. That way, you don't need to put additional fossil feedstock in the system. So the final category for mitigation options would be carbon removal. In the case of, for instance, biofuels, but with carbon capture and storage. So then you have a bit more, in this picture, more complicated supply chain. But the idea is you produce the biomass, process it, spend in your car, in your ship or plane, and while processing the fuel, you try to capture the carbon dioxide. So if you burn it as a fuel, then it's not possible. If you burn it for electricity purposes, then you can actually isolate the carbon dioxide, but then you might have to need to find other ways of putting that electricity in your vehicle, either through batteries or by converting to hydrogen or other carryable fuels. So the problem here and the relevance to energy is if you want to embed carbon dioxide into your fuels, it's quite difficult in energy terms, because carbon dioxide is happy where it is. It is quite a stable molecule, so you need high energy starting materials to make the conversion. For instance, in the case of methanol, you might need a lot of hydrogen to make it happen. Hydrogen doesn't happen naturally, so it just doesn't stay by itself. So you need to actually produce it yourself through other means. But if you manage to do that, then there are a lot of options for you to produce all these fuels and chemicals, just starting from carbon dioxide and hydrogen, using syngas, and through different processes, you can obtain all these chemicals and fuels that we desperately need for the modern way of living. So then these can go into different buckets. They are all being used for different purposes. So there are a lot of possibilities given that you have the energy to start at the first place. So since hydrogen is quite important, I will go over this concept, the concept of carbon abatement energy with the hydrogen example. So the conventional way of producing hydrogen is either through steam methane forming using natural gas, obviously, or you can also gasify the coal. And that's how it is being produced right now, most of the time. And it almost results in 1 gigatons of carbon dioxide equivalent of emissions, because all the industries might have some use for hydrogen, and it just comes from fossil fuels most of the time. So the alternative way is using electrolysis. So in this concept, you have water and you basically separate the hydrogen from the oxygen by using energy. In the case of renewables, you do it through electrolysis using electricity, but you also have other options like nuclear, like thermal cracking of water molecules as well. So the way that we try to understand which pathway is better is we lay down the options on this graph that you will see in the middle. So you try to look at different procedures, understand how much emissions they cause per hydrogen produced, and what is the energy cost of that hydrogen being produced. So here you're seeing the conventional way of the steam methane forming in pink diamonds. And then you have the solar and wind options through electrolysis, and then a variety of nuclear options in purple right-handed triangle. So once you have this basically playing field, what you can do is, okay, I have a reference case of using methane. I want to switch. So which one is more beneficial? So then you can create this carbon abatement energy diagram on the right side, and that will kind of give you a mean value of extra energy you have to spend by switching to different technology. So just to, I guess, explain a bit and put some disclaimers, in the case of steam methane forming, for instance, the values you see, they are life cycle assessment studies, and they kind of show the whole impact of the industry, as well as for solar and winds. But in the case of nuclear, that energy and emissions you see comes from actually the process itself. So the preparation of the nuclear fuel and how much energy basically you have to spend through that to produce the hydrogen. So it actually doesn't cover the infrastructure costs. So what you would expect is the cost for nuclear in terms of carbon abatement energy will go up a bit once you include those as well. But the idea here is, if you bring back the decision diagram that we discussed, then you can kind of understand how these new options are helping you, or whether they are helping or not. So if we kind of broaden our perspective and look at a lot of options as much as possible, then we have these 3 categories that we discussed with kind of different alternative fuel, either alternative fuels themselves or underlying enabler technologies. For instance, if you need a lot of carbon dioxide, then direct air capture or BECCS might be relevant. If you need hydrogen for synthetic fuels, if you don't use it as a fuel but you want to convert, then you need to consider hydrogen. Or if you need electrolysis for low carbon electricity, that's there as well. So what this achieves is you basically try to understand what technology you have or what technology you might have, and relatively consider what is the energy requirements of this. And here the important thing to note is these are path dependent. So these values that you find really depends how you compare these products or services that you're looking at. For instance, in the case of low carbon electricity, we are comparing against coal or natural gas. For hydrogen, as we discussed, we were switching our steam methane reforming to the electrolysis from renewables or hydrogen. and so on. So for methanol, for instance, we do the direct hydrogenation, but there are other routes as well. So the choices I'm showing you here is actually what we have data for. And one particular problem is we don't know quite enough about all the different emerging options, or even for some of the existing options, because the studies are hard to come by. That's kind of, shows all the emissions impacts and all the energy input that that you need for the system. So maybe one last thing to note there is you can see the thermodynamic limits as well. It's not possible to define that for all options, but for the processes that use carbon dioxide directly, either to capture in the case of DAC or to use it in products, it's possible to calculate. So then if you look at methanol, the red line is showing you the theoretical limits of actually producing a methanol molecule, and the individual studies are showing you the real life efficiency. So basically the difference between those lines and the dots are telling you, okay, this is the real life engineering inefficiency that we have, which you might be able to improve, or it may be that you don't have better technology, and that's the energy loss that you might have to accept if, for instance, you use methanol as a fuel. The other thing is, for instance, methanol uses a lot of hydrogen, and in these studies, they are assuming hydrogen is already emission-free. So if your hydrogen source is not emission-free, like like the case right now, then actually you might have to add that energy requirement on top of that to mitigate that much carbon dioxide as well. So it might get complicated. For instance, if you look at dimethyl carbonate, that uses actually methanol, and in these studies, these methanols are considered emission-free. So you have some kind of cascading effect here. So there are a lot of studies needed to understand the energy and emission implications altogether. So one discussion to be had is like how actually we need to consider this metric in general, because obviously it's not answering all the questions. It's answering part of the problem maybe. And as we were discussing, the real problem is if you want to evaluate the technology, hoping that it will replace an existing one or a brand new technology that will give you a different service, you actually have to know how you will do it, and you have to model how it will unfold in the rest of the energy system. Only by then you can actually build these carbon energy balance diagrams and kind of compare whether they are relatively helpful as well. In addition to that, you also need to have a good understanding of different things, like the most fundamental probably in the discussion of climate change mitigation is the potential, the scale of the mitigation potential a technology has. So in the case of hydrogen, we were saying if we basically use emission-free hydrogen today, it could help us mitigate up to 1 gigatons of carbon dioxide per year. That's relevant because we need to reduce our emissions to 25 to 30 levels by 2030 and kind of net zero towards the middle of century. So only a unit of gigatons of change would be relevant at a global scale. And you have to consider if you have big solutions to your sustainable fuel paradigm, that has to match the scale as well. The other thing is the depletion of other critical resources. Maybe it's a bit weird to call land and water as a resource, but it is what it is for us. And also materials that we mine out of the ground. If you want to, for instance, electrify everything, you have to consider what is the impact on, well, land through mining or your ground water resources, and that is not captured in this metric, obviously. And the other thing is there are other considerations that you have to make, like the biodiversity element, which is inherently linked to the materials aspects. But still, that's something you might have to consider separately. And also an equitable transition, meaning that some of these technologies might be possible, but it might be so expensive that some part of the society is not able to reach. So you have to make sure it's universally usable as well. Otherwise, you will lack the impact that it will have. And also, obviously, it won't be possible to define it as an equitable transition. So I will slowly conclude with some discussion points. Hopefully, it might trigger some questions as well in the chat later on. So I guess 3 things that I want to mention in this topic is, 1, is it useful to consider only the technical improvements in isolation? Let's say if you look at the carbon abatement energy of low carbon electricity, so you can use it maybe in electric vehicles and everything, but you're only looking at the supply side of things. And without the context, you might not be able to judge that technology or technical improvement properly. So for instance, a relevant example is what we do with the electricity if we have it from low carbon sources. Right now, we are having a virtual meeting. So the usual way used to be last year that we commit to places and we actually meet in person, which required maybe some form of fuel if you're coming from far away. And that could be maybe done by, I don't know, electric trains. So this improvements could help in that sense. Or right now we're using a lot of data centers and streaming. If you have low carbon electricity, then actually you're also mitigating carbon in that sense compared to the fossil fuel options. So just looking at the carbon abatement energy of electricity might not give you the full picture. You might also want to look at the demand side and understand what are you using this energy for. And then you can actually calculate a carbon abatement energy of the action that you're doing, other than that, just the technology itself. Because I suppose nobody wants to buy electricity to store it as a souvenir. So then with this mindset, you can start to look at the supply side and the demand side, and you can try to understand different pathways for people to take actions that depend on sustainable fuels. So maybe producing ammonia in a sustainable way is a key, but you don't understand that unless you understand the demand side. What is it going to be used for? And what is the scale? Because as we discussed, if we will only have one ammonia ship in the world, maybe it won't matter to produce it in the first place. So the other point is, right now the energy supply is inherently linked to emissions because most of our energy is coming from fossil fuel sources. But that will hopefully fall with time. At least that's our goal at the moment. But does that make it fine? Basically, does that make it justifiable to use very energy-intensive processes to produce our fuels? Meaning that if we need hydrogen to produce methanol to burn it somewhere, it will have a huge energy footprint. And let's assume we have a lot of solar power, wind power lying around. Okay, maybe we can actually produce that without a technical issue. But would that be fine if we consider the side issues, the side effects that we were talking? And one of them is obviously mining. Here you see a map of the world with the critical mine locations. Well, these are critical materials for enabling renewable energy technologies and other commodities. And in the purple, you see both of them together. So you have so many mine properties around the world, and the distribution of these sites are not always in the parts of the wilderness that you might want to sacrifice for the needs of humans. Sometimes they're either protected areas or very critical biodiversity areas. So if you unlock a technology that needs a lot of energy, that needs a lot of mining, you might actually have other consequences of that, even if you can actually do it in other means. And a final point, again, to think about is the low carbon fuels, sustainable fuels, are expensive because we are developing it. We need a lot of research and development budgets. We don't have the necessary distribution network in place either. For instance, if you want to burn hydrogen in your house for heating your house, you don't need the hydrogen pipeline yet. You don't have the hydrogen pipeline yet. So those will be put in place if we want to make it happen. So someone has to pay for it, but there's no clear indication what is the business model for these low carbon fuels, because the fossil fuel counterparts are quite cheap compared to those sustainable fuel options. So how we can make it happen? One is obviously to implement some kind of carbon cost, which has been a tough question and problem that is still in the works, I would say. So other things is obviously subsidies through government measures. It can be even in emergency measures if we really need to cut down and we get serious and we say, okay, we need these fuels in place because otherwise the climate change will be catastrophic. That it will be even more costly, which is probably the case in the first place. Or you might achieve abundance of very cheap renewable energy. Like in the case of California, you might have to actually curtail a lot of your solar power. That actually producing these costly fuels might get very cheap as well, albeit the mine, for instance, issue that we were just talking. With that, I will conclude here, and yeah, I would be happy to take any questions if you write in the chat.
Excellent. Thank you very much for that, Oytun. Really interesting presentation. So to remind everyone watching that you can submit questions through the Q&A box, which you'll find on the right-hand side of your screen. I'll pass back over to you, Oytun, and you can take a look in the Q&A box there.
All right, let me just open that. Okay, I guess the question is carbon abatement energy as a metric versus carbon debts. That's we usually talk about. What are the benefits? So the issue here is you might have different measures to reduce your carbon dioxide, I guess, carbon footprints, or the equivalent emissions that you cause, for instance, through methane leakages and such. But the problem is we also have an energy budget. So it's not always obvious to approach the issue from a carbon debt point of view, because you might not have the energy to take care of the issue unless you have the resources to do so. So that way, the consideration of energy is a critical input to this kind of discussion around climates, because that kind of shows, for instance, some developing countries, they might not have all these abundant energy sources in the first place, and maybe that's why they will linger and depend on fossil fuels more longer than you wish them to. So if you enable a technology, you would like to look at the CAE, the carbon abatement energy of a technology, to see if actually, for instance, such countries can pick it up quite fast, as the developed countries might do. So Nico says, what would you say are the main implications of a research for how we achieve net zero? So that might kind of be linked to the answer that I just gave, but we don't usually talk about the energy budget. And to achieve a net zero, we cannot just assume we have unlimited energy in the first place. At least right now, we don't have abundant renewable energy just in the system. We're kind of desperately trying to decarbonize the electricity sector, which is in the works, almost there, but still we have the options to make it happen. But in other sectors like sustainable fuels would matter, we don't quite have all the technology needed. So when we kind of invest the research development efforts and the funds in different technologies, the implications of the research that I showed would be, okay, you want to monitor the progress of different technologies and how they compare to each other. You can do it through technology readiness levels and other metrics. So this is just one of the other things you might plug it there. Take a snapshot of the system at the year that you are curious about, either now or the future improvements, and kind of understand which technology might inherently help you, and put the efforts toward that direction, I would say. So Fernando asks, what do you think about reduction of carbon dioxide emissions at eco-industrial parks? If the question is how they could be achieving kind of net zero emissions, that will basically depend on what kind of industrial park it is, I would say. But it depends on the sector, right? So if we lay aside the steel and cement industries, and I'm not sure if you consider them in your eco-industrial park definition, the other sectors are quite possible to decarbonize if we have abundant hydrogen in the first place to make all the chemicals that these industries need. And for instance, also high quality heat, because high quality heat is a real problem. And I guess right now the solution is using natural gas. But we need a replacement. For instance, hydrogen, abundant hydrogen could be one of the solutions there. So obviously the discussions around hydrogen is not new, but it's just there is renewed interest and technological development around that. So that could be kind of a way to reduce emissions there.
I can't see any other questions there. We'll just give people another couple of seconds to put them in. This is the trouble. We don't know if people are writing. You know, it's not like they can put up their hands.
Yes. And I mean, also it's difficult to answer the questions properly because we have limited interaction.
Sure. Okay, well, I think if there are no further questions, I'll just say thank you very much again to you, Dr. Oytun Babacan, and also to everyone who joined us today. And of course, the webinar has been recorded, so you can catch up on our YouTube channel or send it to somebody who couldn't make it today. And Simon just says thanks very much for the presentation, and he said he needs to read his paper to get his head around the metric. There is one last question there. Is it possible to consider how the CAE of different options will change over time, or is there not enough data on this? I don't know if you want to take that one just before we wrap up.
Yeah, sure. It's actually a very on-point question, because this kind of metrics they depend on previous studies. So, for instance, the data and the discussions that we were seeing in the slides, they depend on like life cycle assessments or process design studies from like 5 or 10 years ago. So the technologies change much faster, but we're not able to kind of put that in our metrics. So it's certainly a problem, and I guess part of the discussion to be had, but the transparency or the increased effort of kind of accounting for energy emissions and other material requirements of technologies are an important one, if such metrics actually help us in the future.
Okay, great stuff. Let's leave it there for today. Thank you again, Oytun, and thank you everybody for joining us, and have a great afternoon.